Here we are for yet another little bit of asked for revision. Redox balancing. Balancing redox equations. Kind of two basic methods. Well, you can go for the old-fashioned count up things and count up things, but there's two sort of specific approaches towards this that are not applicable to some other equations perhaps. The two methods are here. Combine half equations, so you have a pair of half equations, one releasing electrons, one taking them in. You make sure that by multiplication you get equal numbers of electrons. So equal numbers of electrons released and taken in by multiplication of the entire half equations. And then you just put them together and the electrons disappear and you've got a balanced equation, because ultimately this is about balancing equations. A slightly more convoluted one is the second one, oxidation number balancing. This is the one that people find a little bit more difficult, but when you're presented with an unbalanced redox equation, you can't do the first one because you haven't got the half equations. So you're going to have to go for the oxidation number balance. And here's the three things you have to do. You have to equal up the amount of plus oxidation number and minus oxidation number, meaning plus oxidation number is oxidation, minus oxidation number is reduction. So there has to be, and the total increase has to be equalled by exactly the same size total decrease. So there's no overall change in oxidation number, you could think of it like that. What then happens is often, unless it's a very simplistic system, which you may not need to go all fancy about it, but if you can see that, but what to do, once you do that, you often end up with hydrogen deficit or oxygen deficit, and you have to use hydrogen ions and water usually. Other things sometimes do. Hydroxide ions are the next on the list of things that you use, but occasionally other things. Not likely to see the other things. Almost all A-level ones are water and H+ to massage the left and right to get them to equal. And you do a little check at the end that you've got a total charge on the left identical to a total charge on the right, and therefore you haven't lost electrons on the way. Now, those two methods, they are actually facets of the same thing, because electrons cause oxidation and reduction, and obviously the oxidation number changes are reflecting those electron movements. So therefore they are kind of two methods of doing the same thing, but you go about them in very different ways. We'll do some examples of this, and then we'll do some examples of that. These ones tend to be a little bit more tricky when they get quite complicated. Got to keep a clear head. But right now I'll get the board ready for some half equation ones. I'll see you in a moment. So here we are with two relatively straightforward examples. Top one, silver has taken in electrons because it's less reactive. Zinc is more reactive, so it's releasing electrons which the silver picks up. 2 electrons against 1 electron, so that whole thing needs doubling. Alright, so 2 Ag plus, but we can ignore, because we've equalled the electrons up, we just don't write them in. So it'll be 2 Ag plus Zn solid. Put the state symbols in. It's the only one I'm going to put state symbols in. Save a bit of time. And then now you may not really have needed to think, oh, I'll have half equations and put all that together, because if you just wrote that out you'd probably be able to balance that fairly straightforwardly. However, it shows the point. Equal numbers of electrons, doubled up to get the same number of electrons in here. Here's another example, example 2. Very much not equal electrons. Now we've got aluminium having 3 electrons to convert it into aluminium. See, not bothering with state symbols anymore. It's kind of the electrolysis of aluminium. And then two oxide ions combining to make an oxygen and releasing 4 electrons. Now 4 and 3 are obviously not the same number. How do you resolve when you've got that kind of difference? Is you basically go, what's 4 times 3? It's going to be 12 electrons. So you've got to get that to be 12 electrons. So that whole thing goes times 4. This one times 3. Board not big enough. So you've then got 12 electrons in each one. So you've got the same number of electrons. Now sometimes you might do that and go, when you put it all together you can divide, but we'll see whether we can do that or not. So 4 aluminium 3 plus, 12 electrons, which we're going to ignore, 3 lots of 2, which is 3 lots of 2 oxides, that's 6 oxides. Then we get 3 lots of O2, 12 electrons is what we're trying to ignore, and therefore we must get 4 Al there. Is there anything you can divide all of those by? No, so that's the balanced equation. Does it matter which order you have these two in? Or those two? I don't personally think so. Maybe somebody does, but I don't. So they're fairly straightforward examples. We'll do a little bit more while I get the board ready. See you in a minute. So here we are with two increasingly complicated, particularly this one, examples, and we've been joined by some rain clouds and some thumping down rain. I don't know whether you can hear that. So the top one, reduction of Fe3 plus to Fe2 plus, and then there's an oxidation of a sulfate 4 to a sulfate 6, and obviously not the same number of electrons. This one here, I'm going to do this doubling a different way. I think I'm just going to go 2, 2, 2 this time. You do it either way. And then sum the two things together. So and there it is. Are there hydrogen ions on both sides? No, so there's no cancelling out to do. Same with the water, there's no cancelling out of water to do, which is something that does happen in the next one. So there, that's it, that's balanced. It's no more complicated than the other ones, other than you've got all these other things to consider when you do the, the putting it all together. There's no doubling up of this one, fortunately, but it's not going to be the case with the next one. So let's go on to this last and somewhat more complicated example. We've got, this is a thing called thiosulfate, which you may have met, usually in iodine titrations, and that's a sulfate 4 again. Here we have a chromate 6. It's like dichromate but not dichromate, which you probably have met at one point or another. And there's a chromium 3 hydroxide. It's done in alkali conditions in both, because there's OH ions in both, hydroxide ions rather, in both. So when you look at the number of electrons, 4 electrons in the top one, 3 in the bottom one. 3 times 4 is going to be the way to go with 12 electrons. So it's going to have to be 3 times the top one. So 3 so it becomes 3, 18, 6, 9 and 12 electrons, which will vanish. And then it's 4 times the bottom one. So that becomes 12, 4 there. I've got room to get it in. That 4 becomes 16. That becomes a 4, squeeze that in there, and that becomes 20. Quite big numbers, but something's going to happen to some of them anyway. So the next thing to do is to sum it all together, and there'll be the same things on both sides this time. But we'll see what we have to do, but let's just get it down there. I'm just going to get them all written. That was big. Not enough room. I hope you can read it. Kind of needed a bigger board, turn it sideways maybe. Now, that as it stands is technically balanced, but balanced poorly. So what you then go is, I've got 18 hydroxides there and 20 there. So those 18 can all vanish, and that just goes down to 2 left. And you've got the same thing with the waters. You've got 9 waters there and 16 there. So all of those 9 cancel out with 9 of the 16. 7 left. So that's 16. Becomes 7. And that kind of sort of simplifies it significantly. It doesn't change the number of thiosulfate and the chromates and things, but so water has gone from one side, hydroxide has gone from the other side, and there we have the somewhat simplified balanced equation. It's got some quite big balancing numbers in it for A level, and yeah, you do kind of look at that and go, so if you want to convince yourself it's balanced, you count up the number of oxygens, count up the number of hydrogens, along with count up everything else just to make sure. Also the total charge on one side should be the same as the other. So if we got that right, 6 and 8 is 14, 6 lots of 2 is 12, 13, 14 with the hydroxide, this being uncharged because it's a substance. So looks like it's balanced, there we go. And then we'll go on to the other method, see you in a moment. Okay, so moving on to the oxidation number method. 5th example, first one of these. Here we have vanadium being oxidised to a thing called VO double plus. And here we have a rather unusual looking thing, which is mercury as a 2 atoms joined together. It's a weird, but mercury does lots of odd things. I mean, it's a metal that's liquid at room temperature. I mean, you know, there's plenty of odd things about mercury. And it becomes mercury metal. So this is an aqueous ion. This is not a solid because I've just said it's a liquid. And then that's a liquid. The vanadium ions are aqueous along with the hydrogen ions. Now, looking at that, you go, oh, it's got the same number of oxidation and reduction. Yeah, but it's not. Because when you look at the formula of that, when it says Hg2, you cannot but avoid 2 Hg's coming out of it. So that means that this is now happening twice. 2 mercuries are being converted from the ionic into the metallic state. So you've got a -2 change. That means that you have to have a +2 change up there. So as soon as you do that, that's got to be doubled and that's got to be doubled to give you 2 vanadiums going up by 1 oxidation number. If you don't know why that's for, you kind of need to review how to calculate oxidation numbers. And if at any point in these you go lost, rewind it, watch it again, maybe get a pen out and make some notes, stop it and start it. You might like to do that over the first 4 examples, particularly the last one. So here we then have the required oxidation number balance. What you then do is look at, okay, oxygen's a good way in. How many oxygens have we got there? 2. No more oxygens out of these things here, but there are 2 oxygens. Now the only place you source oxygens on the left hand side is water, so there needs to be 2 waters. And when you look at that, you go, now there are 4 hydrogens, which is the next stage on, 4 hydrogens So you've got to have 4H plus because there's nowhere else where the hydrogen ions appear on the right hand side. So that then means that the balanced equation,
and I said I wouldn't do state simples, but I'm going to show off and do them because I do know what they are.
the balanced equation is that. Do you need to get rid of hydrogens and waters from both sides? Water is on that, there is no water on that side, so there's no cancelling of water. Hydrogens are on this side, none on that side, so there's no cancelling out to do. That is the balanced equation. Done. Going to do another couple before we get to the end of this video. So, and then maybe you'll do some practice. I need to get the board ready for the next one. I'll see you in a moment. So, here we are with a marginally more complex example than the previous one, but it's one of A-Level's favourite redox reactions. It appears in core practicals, usually as a titration of iron sulfate tablets, iron tablets for low iron in the blood, and therefore it's a candidate for paper 3 first of all. Secondly, it's also a redox equation, so there's a balancing thing. There are two redox reactions that are the favourite two for A-Level. This one, and the other one is the iodine thiosulfate, which is also used in redox titrations. I would say learn both of them off by heart. Save yourself the pain of having to work it out in an exam. You just meet them so often, just get them in your head. However, here we go for doing this one in the way we're supposed to. Manganate 7 ion over there, manganese in a +7 oxidation state, is reduced by 5 down to +2. So it's quite a long drop. That's why it makes manganate a powerful oxidising agent for a number of other things. Fe2 plus is oxidised by a 1, loses another electron in other words, and goes up to 3. So in order to balance it, that needs to be 5 times the size. So you need a 5 in there. I didn't leave space. And so that immediately sorts out the redox part. The oxidation and the reduction is now equal amounts of both. However, we've got a bit of an issue with the oxygens. So what do we, I usually go oxygen first, hydrogen second. So oxygens, on the left hand side there are 4. We need 4 over here. The only way to achieve that is make 4 waters because they don't appear in those two species. So as soon as you've got 4 waters, now we move on to the hydrogen. There are 8 hydrogens, 8H plus. So this is the equation worth learning. Now we're going to do a charge check on this one. I can guarantee that the hydrogens and oxygens are now the same because we've just done it. We're going to do this, what I say we should check the charge. I didn't do the charge check on the vanadium example. You can go back and have a go, it's relatively straightforward. So here we have got minus, actually that's, -1 would be an oxidation number. Minus before the 1 is oxidation number. Afterwards is a charge. Oh, it's not 1 plus, is it? Oh, hello. It's not 1 plus. Let's do that again. Right, so it's a 1, that looks like a fallen over T, doesn't it? Moment of disaster in the video. And then 8 plus, and then 5 lots of 2, 10 plus. So you add all that lot together, it's 18 plus and a minus, 17 plus. Do the same over here, 15 plus, 2 plus, water, no charge, put that lot together, 17 plus. That's what I mean by make sure the charges are equal left and right. And that's it. that's that one done. Number 6, example 6, there we go. Worth learning along with the iodine sulfate titration equation, because one of those two is pretty much guaranteed to be in a paper 3, I would say. I'll see you for the last one. Last one, a little bit complicated. So complicated I had to get a new pen with a nice pointy point to get the writing to fit across the board. Ooh. So, first of all, what have we got? We've got ordinary nitrate ions, nitrate 5, which is why they're +5 over there, reacting with arsenic, elemental arsenic, it's not a metal, and it's under acidic conditions with water, and then it produces HNO2, so that's a nitric 3 acid, so there's a reduction of the nitrogen in there, goes down to 3, so it goes down by 2, and then the arsenic becomes an arsenic acid, which is HASO2, so it is a +3 state, so there's an oxidation of the arsenic, and it's got H+. Now, what's going to happen in the end is from one side of the equation water will vanish and the other one hydrogen will vanish, but as it stands you don't know which one it's going to be. Now, why are they there at all? Because I took these from a pair of half equations, and of course individual half equations, they don't know they're going to be meeting up with something that requires cancellation until you actually put them together. So I've got everything present and then we'll see what happens. So the first thing is the oxidation number balance bit. So nitrogen comes down by 2 and the arsenic goes up by 3, not the same number, so 3 times 2 is 6, so we're going to do 6 oxidation number change, so we need 3 of the nitrogen change, which is why that 3 is there and there's a 3 in front of the nitrate on this line here, and the arsenic has to go twice to give you 6, which is why there is 2 arsenics and 2 HASO2. I realise this writing is small, but my board is of a finite size. So, by doing the oxidation number balance, we get this. I said to you, oxygen first, hydrogen second. That's what I'm going to do. I'm going to count up the oxygens. So when you count up the oxygens on that side, there are 9 in the nitrates, because there were 3 nitrates, and there's an extra 1 in the water there, makes 10. When you count up the oxygens in these 3 things here, 6 plus 1 plus 4, 6 there, 1 there, 4 there, it's 11. The oxygen count isn't the same. Now the only way to resolve that over there, sensibly, because you can't mess with something that you balance the oxidation number for, because that's the point of oxidation number balancing, is it fixes that and then you work the rest of it out by not altering the balance of oxidation numbers, is that the only way to do that is to put a 2 in front of the water. So that then becomes 11 oxygens. Then we need to do the hydrogen ions. So now when you count up the number of hydrogen ions, if you're eagle-eyed, you may have noticed that this wasn't true until now, but it's true now. There are now 5 hydrogens there, and over here currently we've got 8. So we are 3 deficient on hydrogens on that side. So what we need, we've got 1 there, 1 plus 3, oh, difficult question of the day, is 4 H plus. So nominally balanced but clumsily balanced because you've got the same thing on both sides. So what do you do then is you get rid of the things that are cancelable. So water there will get rid of the balancing number on that water and leave you with 1 water. The hydrogen there will cancel out 1 of the hydrogens on there and leave you with 3. So the final equation, by losing a couple of species, got a little bit more board space to play with. Don't get complacent and write too big. That's my message to myself. So we've checked everything through to hydrogens. The last thing is a charge check. Charge check, 3 minuses, 3 pluses, nothing, 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 so 0 on that side, 3 minus, 3 plus, put together, 0 on the left hand side, 0 on the right hand side, all good. There's the balanced equation. So that turns into that. That is, if you've got something that complicated at A level, it would be a pretty hard thing to have in terms of a question on the paper. But on the other hand, they do have to ask difficult things somewhere in the paper in order to give people A star and A grades. So there you have a quite difficult oxidation number balance involving juggling the oxidation numbers, doing a sort of cross multiplication thing of one number against the other, the 3 and the 2, sorting out an oxygen imbalance, then sorting out a hydrogen imbalance, then cancelling out common species on both sides, reduces it down to that, which has the charge balance that we need. Hopefully, if you go back and review, I suspect this last one you might need to play it a second time, and maybe look at some, go back to some of the others, make your own notes. We might need a bit, maybe not a bit clearer, but a bit more. You can always come back to this video to hopefully don't go away. I don't know much about YouTube in terms of longevity. And then you can have a go. I'll write some questions, I'll attach it to the video, and then you can have a practice with those as well. Person who asked for this, hopefully you're very happy, because this is what you asked for. Everybody else who's watching, thank you for watching. I'll see you soon. Bye.